So your goal here was to show that if we have a finite cyclic group that has an even order, and I pick an element of that group whose order is odd, then the order of that element is the same as the order of its square. The order of g squared is the same as the order of g. And so what this group has done here is they've put some names to some of the things that are alluded to in this definition. They're calling the order of g 2L, because it's an even number. We know it's twice some integer. They're picking out a generator of the group, calling it A, and we know it has a generator because it's a cyclic group, and making the argument that the order of A, the generator, is finite. We know that because the order of a finite cyclic group is the same thing as the order of one of its generators. So by the way, hint, hint, that sentence that I just said actually establishes a relationship between these two numbers. What's the relationship? They're not just equivalent, they're equal. Yeah. The order of a generator in a finite cyclic group is the same as the order of the group. Because that element has to generate every element in that group, including the identity, that means that it has to take exactly n steps before it comes back to the identity. Right? When I take steps, I mean powers. So actually, n and 2L are equal. So that could be valuable later on down the line. This team has also brought out the assertion that because G is a cyclic group, the order of any element in the group will divide the order of the group. Okay? That's something we established in one of the videos for cyclic groups that they didn't use in this part of the argument, but again, may be useful for a later part of the argument. And so then after that, what they're able to show is if the order of G is 2m plus 1, so it's an odd integer, so it's twice an integer plus 1, that the order of G is the same as the order of G squared. Well, almost. Because they showed that the 2m plus first power of G squared is equal to the 2m plus first power of G, which is equal to the identity. Right? So just to kind of annotate on the side of what they showed here, was they showed that G to the 2m plus 1 equals identity implies that G squared to the 2m plus 1 is equal to the identity. That doesn't show that the order of G squared is equal to 2m plus 1, but it does show...
Can they have 2m plus 1 for both sides? Because that would be saying that they're the same number order. And wouldn't you have to use like 2m and then 2n? So they're both odd numbers, but they can't be the same variable because then you can sort of see that maybe they're the same number.
So I don't see a problem with that here, and here's why. So the group is defining m on this line here, right here. So m is the number which defines the order of G to be odd as 2m plus 1. And then once that happens, all they're doing in this line, this long line here, is they're just doing an algebraic computation with m and g, right? But the 2m plus first power of G turns out to be the same thing as the 2m plus first power of G squared. And that's okay. We haven't introduced a unknown to represent the order of G squared. They could have done that if they wanted to. They would probably have wanted to call it K or something that's not already taken here. But they didn't do that, and so I don't see a problem with that here. But what this result here shows, the fact that the 2m plus first power of G squared is equal to the identity, doesn't show that the order of G squared is equal to 2m plus 1. What does it show?
Just show the full orders.
Close, right? So the point is, as Brian was saying, about that in order to establish this equality, now that we know that 2m plus first power of G squared gives us E, we now need to rule out the possibility that maybe a smaller power of G squared gives us the identity. So what this showed us is it showed us that the order was less than or equal to 2m plus 1. What we haven't shown is why it's equal, why this is why 2m plus 1 is the smallest power of G squared that gives us the identity. That's the missing link. So if we can establish that next, then we will have finished this proof.